Morning. So I have a big piece of mica someplace, but I can't find it. So I'll pass this around. Don't lose it. If it was larger, you could peel it apart. You could peel that apart, but I prefer you didn't because there's not much left of it. And then if I found a feldspar sample, something to put on the cart, which is great. This is another one, the same composite, but you can let's see the mica in the end. This is probably small enough to pass around. This is also feldspar. This is actually, you could argue, a remarkable sample in its cleanliness. You know, there's nothing else attached to it. And it's pretty good size. The name orthoclase comes from the way that it cleaves, basically. And then this is massive quartz. This comes out of Ontario. In Ontario, Canada, there's a large natural quartzite deposit. And they mine it, crush it. Okay, so it's not sand, it's sort of sand. I'm not going to pass that around. You just have a need. And this is single crystal quartz. These are hydrothermally produced. This is from Arkansas, likely. A lot of quartz in Arkansas. There's also, you know what a Herkimer diamond is? Anybody from Herkimer in the vicinity? Where are you from? Close enough. So it's a Herkimer diamond. Yeah. If it was a diamond, people in Herkimer would have money. They don't. It is a doubly terminated quartz crystal. I have one somewhere. And so they grow in pockets, basically little pockets in sandstone. And what's interesting is that this quartz crystal, the way they grow up that termination spot at the top, the point, is how they grow. They grow upwards that way. And so Herkimer diamonds are unique in that they grow out. So you have doubly terminated, two termination points. How they nucleate and grow, I don't know. Saw in Arkansas one of these where the tip broke off and another crystal formed around it and created, they call it a phantom tip. It actually recreated that tip inside even though it wasn't there, it kept growing. So you could see the inside quartz crystal inside another one. Quartz of that quality is used for oscillators and watches and timing devices or what have you. So there are massive quartz crystals. So when I was a student, we went to Arkansas looking for quartz crystals, and I spent the day. And at the end of the day, I understood where to look. I didn't understand where to look at the beginning of the day. So you get sandstone layers, basically. Water gets in, and then pressure and temperature dissolve the silica, and it precipitates out, grows off of the sandstone. And then what happens is, in a second event, those pockets in the sandstone fill with clay. And they sort of stop that process. And the pressure is gone, and the heat is gone, etc. So what you look for are large clay pockets, because in the large clay pockets are large quartz crystals. And in should be in the thermal analysis lab, there's a massive quartz crystal cluster. Nobody crushes that stuff up for porcelain. Okay, so this is where we're at. I'm going to talk about clay today, basically, kaolin, where it comes from and everything. And we'll get into some other things as well. And we'll also, in the process, talk about feldspar. So you need to keep this in mind. We have rocks and minerals. I think we talked about it once before. But a rock is a collection of minerals. Minerals are a specific chemistry and mineralogy. So if you have the right chemistry, but you have a different crystal structure, it's not the same mineral. If you have the same crystal structure and not the same chemistry, it's not the same mineral. So feldspar, like albite, which is the sodium feldspar, and orthoclase, potassium feldspar, have the same structure but different chemistries. They have different names. Kaolin is a rock. It is not a mineral. It's composed of kaolinite, which is a mineral. And so kaolin actually is a whole bunch of names for clay. Kaolin, ball clay, fire clay, china clay. Those are all terms that are more or less invented. They are really not, they don't really differentiate the materials as being unique. So the origins of that terminology really come out of how that material was used and also perception. So there's a book that you may or may not be interested in. It's called The Arcanum. It's talking about the quest for porcelain in Europe in the 1700s. And you can probably get it now really cheap, for a few bucks as a paperback. It's interesting. So the issue is this, right? China is being produced in China. Porcelain is being produced in China for a long time, and then started to be exported. So during, I believe, the Ming Dynasty, they started exporting China porcelain into Europe. Europeans loved it, and particularly the royalty, and they spent a lot of money that they didn't have to buy porcelain. And then they would go to war to get more money to buy more porcelain. It's kind of an interesting de-evolution of ideas. Anyway, they started a program to develop porcelain in Europe, and they had no idea how it was formed. In the 1400s, China was extensively traveling on the seas, right? They actually saw no need to go to Europe. Europe didn't have anything they wanted. But they would actually hang porcelain pieces on trees on the ship and acting like it grew there, right? Which probably in the 1400s was not that big a stretch for people to believe. But the Europeans didn't understand the origins of porcelain. They didn't understand the materials that were involved. And they started this program to figure out how to get to porcelain. So when you get to the clays that were used, they were looking for white clays, and then they turned them China clays because they were making China or porcelain out of those clays. First attempts to make porcelain that were marginally successful, we call soft paste porcelain. Basically, it was based on alabaster, which is calcium sulfate, not feldspar, and eventually they figured out feldspar, and that then changed more or less everything. So if we look at England, it's a good place to start. So what we have is this. We have a bunch of clays, okay? So you have China clay. You don't necessarily need to keep this in mind, but you're going to see these terms. Kaolin, ball clay, and then we get into something that is a little different, which is fire clay. Okay, so they're all kaolinitic. They all have kaolin involved. They're all have a large fraction of that material is kaolin. And typically, you would argue it's greater than 50%. Usually, it's much greater than 50%. Like in a China clay or a kaolin, it might be 90%. Okay. These are really the same thing, and even ball clay would be argued to be the same as kaolin, except in England. And so, in England, the kaolins were primary deposits, and in England, ball clays are secondary deposits. And they didn't care about fire clay. So fire clay is not an invention in the U.S., but it certainly became prevalent in the U.S. around the mid-1800s. Okay, in the mid-1800s, the reason is that they were Industrial Revolution and need for furnace linings, refractories for furnace linings. Fire clay became really important, and there are significant fire clay deposits in Missouri, for example. I think maybe northern Alabama. And the issue is this, that they are, the fire clay term means that they are typically high in alumina, little excess silica, high melting point clays, but they're really not any different. And all of these clays are very, very similar mineralogically. But in England, is not the case. And in England, it's a different situation because of this history with China, right? So you have England, you have Great Britain, if you will. And we're really interested in this area down here. The rest of it, it's not that it's not important, but in the context of this, actually, a little island off of the coast of Scotland, the island of Mull, M-U-L-L, is where they first discovered mullite. So, a lot of history. There's a really good book called The Map That Changed the World Anybody know it? Simon Winchester wrote the book. He's actually a geologist who wrote a bunch of books. Highly recommend all of them. Krakatoa, awesome. You should read Krakatoa. And you should read The Map That Changed the World. So what this guy did, his name was William Smith. He was in England around the Industrial Revolution, and he mapped the geology of England. And of interest at that time was only one question to people who owned land, and that question was, do I have coal? All right, so Industrial Revolution is getting started, and the demand for coal is huge, and if you had coal, you became richer. Okay, so the coal issue was a big deal. So basically this guy starts his whole career by looking at fossils, and then he could arrange the fossils based on their age, more or less. He could group them. So they showed up in strata. Okay, they, critters died, and then, they got impounded or whatever, buried, and then they built up. So he would come in and organize people's seashell collection or fossil collection, right? And then the idea that the map that changed the world is because this is a fundamental shift, right? Up till that point, it was Adam and Eve and the whole progression, and oh yes, and then the reason that these are here is because God stuck these shells in these places for you to find, basically, rather than a progression of ideas or time. So he mapped all this strata of England and created this map called Geologic Features of England. And England is unique, such a small place. You have all of these different areas represented because of the way that the crust moved, and you get these layers. So that's William Smith, and so it's also interesting in this context. There's a lot of stuff going on in England. So they found clays in these deposits, basically, and the red deposits and the pink are granite outcroppings, and associated with those pink granite outcroppings, not pink granite, but granite outcroppings, the red splotches here are the kaolin beds, the clay beds. And so what you have is that, where does clay come from? And clay comes by weathering feldspar. So granite is a mixture of feldspar, mica, and quartz. Okay, feldspar, mica, and quartz. We talked last period about, this is an igneous rock, right? And it's a solidification event. So quartz comes out first, and then feldspar, and everything that's left ends up going into mica, more or less. The feldspar weathers to create clays, and you can even include the fire clays, weathering events. Okay, so weathering events means that water comes in, dissolves out the alkali, right? And you could argue that you also have some hydrothermal deposition of quartz, but water comes in, dissolves out the alkali, you create this aluminosilicate soup, okay? And from that precipitates out kaolinite eventually, right? And so if the kaolinite that's formed stays with that parent rock, it's a primary clay deposit, so it's not transported and deposited. If it does get transported, which is not uncommon, and so if it does get transported, it gets deposited someplace else, then it's secondary clay. Okay, so your primary clays are deposited with their form, secondary clays are then transported and deposited someplace else. And so what you see here is that these deposits here, the gray ones, notice their locations, right? So the location here, here, those are the bulk clay deposits. So the clays were, I don't know where these came from, but these were probably produced up here or up in here, and they came down and got deposited, and they get deposited typically at the seashore, more or less, okay? Now, in the United States, that is true, except that the seashore is now a long way away, right? So the deposits are in Kentucky and Tennessee, right, and in Georgia, for example, and South Carolina. They're a long way from the sea. There's a reason for that. So these clays were deposited here. The ball clays are deposited here. The kaolins are here. So they're mining these clays, and they termed these clays, the ones that are secondary, they termed them ball clays because they would essentially mine them in large balls, ball-shaped material, chunks, because they were plastic, and they would push them onto barges and take them up the river to Stoke-on-Trent. And Stoke-on-Trent was all the porcelain factories. Okay, and so also the kaolins, though, were mined in more or less typical fashion, shovels basically, and put on carts, taken to the barge and up the river, right, to Stoke-on-Trent. So those are the origins of kaolin, the terms kaolin and ball clay. And in England, then, the kaolin and china clay are really interchangeable. We still get clays from England. And the benefit of the clays from England is that they're very, very white. Did we talk about that in here already? Whiteness, right? The titanium levels are very low in those clays. And so you get very white burning clays. And so people really like that. So they'll pay the price to import clay from England. We have great clay here, but they like that better. So that's the origin. Now what happened in the United States is that clays from Georgia, South Carolina, etc. Okay, so you would recognize this, of course, immediately. In the clay deposits, there's a bunch of them actually, but we're talking about the clay deposits here, and clay deposits here, and in the middle of this are the Appalachians. Okay, so those are the granite rocks that are the source rocks for these clays. And then in here are the Ozarks, and then in this region, more or less in the center of the state, are the fire clays. When you get out west, we actually have a lot of clay deposits out west, not nearly as famous or commonplace as what you see in the east, but there are clay deposits all over the country that are associated with granite outcroppings, mountains basically, all over. There are famous Mount Millenite deposits, bentonites in Wyoming. There are clays in California, there are clays in Washington and Oregon, but they're not as heavily exploited, I guess, as the clays originally coming from Georgia and from Kentucky and Tennessee. And part of that has to do with the history of Western expansion. Right, so they found these clay deposits later. Boston Valley Terracotta is here. They make terracotta. Gladdy McBean is in California. They also make terracotta. And they have a famous clay called Lincoln Fire Clay, I think, which they mine and use to make terracotta, which is not necessarily the best situation because there's a lot of variability and it shows up. Okay, so what you have is kaolin deposits. The two white lines more or less represent what would be called the Piedmont, right? So the Piedmont, I think, comes from the French word, the foot of the mountain type of thing. I don't know that for sure, but I know Piedmont is foot of the mountain. So what happens is, right, these clays are depositing what are called coastal plain sediments. And it says fall line. The fall line represents a change in geography, or if you will, geology. But you have the mountains, and there's basically a change in elevation associated with going to the coastal plain sediments. What you get is waterfalls along that line, as corny as that sounds. But the clays at that time, right, were being produced by weathering up in the mountains. And when they came down to the sea, which the sea was then there, right, so you hit salt water, clays coagulate, drop out of suspension. Perfect situation. And in Kentucky and Tennessee, it wasn't dry land like it is now, well, probably not this week, okay, but it was also an inland sea, or so they said, right? And so you have the deposits on the other side of the mountains in Kentucky and Tennessee, in basically western Kentucky and western Tennessee. These areas here, those clays in Kentucky and Tennessee are called ball clays, okay? And the clays that are in Georgia and South Carolina are called kaolins. And you might ask yourself why, and that's a good question, because there really is almost no difference mineralogically between one and the other. Their formation conditions are nearly identical, probably are identical in terms of weathering feldspar from the same mountain range, and then the deposition process is the same. So in the United States, there are essentially no primary clay deposits that are commercially exploited. there are primary clay deposits. Okay, so and I'll show you a picture of one. There are primary clay deposits. They're just not large enough to be commercially viable. So all of the clays that are mined in the U.S. are secondary clays. But because it's probably Norton or somebody like Norton, F.H. Norton, who came, saw he had an English education. I think he grew up in England. Came to the U.S., became a professor at MIT, saw the clays in Georgia and decided they were kaolins. Or somebody else decided they were kaolins. And the argument is, or was, that those clays were primary clays just like in England, but they're not. They're all secondary clays. And then on the other side, they term those ball clays. They aren't, one is not cleaner or dirtier than the other. One doesn't contain more garbage in it versus the other. It just has to do with how they're processed. So the clays in Georgia and Tennessee and South Carolina are typically beneficiated to remove the quartz. And those clays, most of those clays, go to the production of paper coatings. Whereas in the Kentucky-Tennessee clays, those are ball clays. They don't typically beneficiate to remove the quartz. They do beneficiate to remove stuff like, twigs and, rocks and stuff like that. But they're not really doing the same sort of beneficiation. So you find that the ball clays from Kentucky and Tennessee contain a lot of free quartz, whereas the kaolins in Georgia and South Carolina tend not to. And then there's one more clay deposit which shows up down here, and you know that Florida is entirely a coastal plain sediment. I mean, there's no geography in Florida. There's a clay deposit, I think it's around here, which is EPK, egroplastic kaolin, in Edgar, Florida, also a secondary clay deposit. And we like that clay, it's a good clay. So there are good clays and bad clays. By the way, over here, if we look, there is also, you will find, there are other clay deposits in Mississippi, there are some in Alabama, there are some in Arkansas, etc. There's even clay deposits in Indiana, that's the shaded state up here, but we don't really, they're not very common. They contain a lot of mineral impurities that we find make the clays highly variable and not very uniform in terms of performance. And everything about this is uniformity in terms of performance in the manufacturing process. Okay, so there are the kaolin mining districts in Georgia are identified. There's the fall line. They all sit at the foot of the fall line. Those are the big ones. In Georgia, it's called white gold. And if you happen to have clay on your land, you never have to work again because they'll come and they'll mine your land and pay you for every ton of clay they take off your land. And so that's a way, that's the golden plum, right? So I've been to the clay mining districts in Georgia. There was an international clay conference that was held in Ottawa, Canada, and the field trip was to Georgia. It's like to go see the clay deposits. How cool is that? So went to Georgia, and then and I'll explain that in a minute. So anyway, this is where they show up. And the source rocks for these materials are up here someplace. And a friend of mine, Tom Dombrowski, who I met on this trip, we had interacted a little bit previously, and he was he worked for Hamill and Gillespie, I think it was. Big company, $2 billion company. $1 billion of their worth was in paper clay. So it was a big industry. And they had all these mines and they had these problems. And so I was down talking with Tom. But what Tom's thesis was is he looked at the mineralogy of clay deposits and actually trace element chemistry, and then looked at the source rocks and drew a correlation between the trace element chemistry in the source rocks and the trace element chemistry in the clays, and identified that where these clays came from in terms of their source rocks, where was the granite that produced these clays, basically. And he came up with something very interesting, and we're going to get to that in a second, but it is, you have coarse grain and fine grain kaolins, coarse grain and fine grain clays. Coarse grain clays come from coarse grain granite, fine grain clays come from fine grain granite. Very simple idea that not commonly appreciated prior to Tom. So we already did this. These are the common mineral impurities. So you don't need to necessarily pay attention to the specifics But quartz is your primary impurity. And if you took a clay, I'll show you a picture in a little bit. If you took a clay and settle it, if you disperse the clay, all the quartz particles will settle out. They'll show up in the bottom. And they're relatively large. They're on the order of 50 to 100 microns sometimes. Even if they're 20 microns, they're going to settle at a rate significantly faster than a 1 micron clay particle, right? So what you can do is separate that clay fraction, or the quartz fraction. And then what we did was looked at the mineralogy of these clays. So there is something that shows up uniquely in the ball clays, and it's called, we term it, 14 angstrom mineral, and that means that the spacing between the layers is about 14 angstroms and doesn't fit any known X-ray diffraction patterns. We were not the first people to find that, and when we reported at a conference, there was a general consensus of, yeah, we've seen that, but we don't know what to call it. Right? So there is that sort of a unique mineral that shows up in the ball clays, but it's a small impurity. So the idea that we had here was that if we were to segregate by particle size, we could concentrate in those sediments small amounts of impurities that would make them detectable. Right? So if I had 2% montmorillonite in a clay, my X-ray diffraction pattern will be mostly diffuse and I won't get much out of it. If I can concentrate that 2% into a smaller fraction, it becomes, say, 20%, then I can X-ray to determine it. Make sense? So there are techniques you can use to improve your resolution. Illite is essentially a kaolinite that contains potassium. And what happens is that in weathering events where the water does not drain very well, so it sort of sticks around, you will start to incorporate that potassium, which you have dissolved out of the feldspar, back into that clay structure in some fashion or other. So you end up with illite. And illites are common, not common here. And the reason they show up here is because the illite particles, in this case, attach themselves to the quartz. So they show up in the quartz fraction. They're actually very fine particles, but they are agglomerated on the quartz. We don't really care too much about that. So the message from this is that, yeah, there are some minor differences, minor differences between the ball clays and kaolins. We don't care about that. The primary impurity that we see is quartz. So therefore, that analysis that we did earlier, the LOI, looking at the loss on ignition and estimating the free quartz content, is valid, and it's going to basically scale with your other impurities in the system in terms of being off by a few percent or whatever. It works really well. It's very effective. Two types of kaolin come out of Georgia and South Carolina. There is a coarse grain, soft kaolin, and a fine grain, hard kaolin. So the history of clay mining in Georgia is that one guy owned all of the clay in Georgia, and he formed the Georgia Kaolin Company. He owned all of it, and he had the poor foresight to die without a will. Okay, I'm not sure that dying was part of the picture either. However, the problem was that he really had a monopoly on clay in Georgia, but he didn't name a successor or an heir. So now it created a problem and went to the courts, and they split up the Georgia Kaolin Company into about a dozen clay companies. And they're all, dispersed throughout Georgia and probably into South Carolina. And so Georgia Kaolin Company, when I was a student, Georgia Kaolin Company was still around, and now it's gone. But you'll see GT or GK, Georgia Kaolin, on bags still, if you have old materials hanging around. Teal kaolin, Albion kaolin, Wilkerson clay, Imerys became a part of that. I mean, all these companies grabbed up parts of the Georgia kaolin. Now, the guy who started, I don't know his name, I probably should know. They were pretty sharp. And they would go around and mine or do sampling. So, and they would look at the quality of the clay deposits. What do you mine first? The best one. Best quality you mine first. And then, which actually is not a bad philosophy or a business approach. There are these spectacular clay deposits. You start mining the clay that looks the best first, and then as your technology improves, you can mine clays that aren't as good but beneficiate them to get a high quality clay. And so you will hear periodically, the Chicken Little syndrome, the sky is falling, and we're running out of clay. We will never run out of clay. I mean, there is a lot of clay in Georgia, right? It's just a question of quality, and what they have been doing over time is improving the technology that they use to beneficiate the clays. And you will hear people talk about, oh, that used to be a great clay. That is all nonsense. These clays are all really pretty spectacular. But the soft, coarse-grained clays were really highly sought after because you put them in water, they easily redisperse. So they're really easy to process. And the fine-grained hard fine-grained clays, they take more energy and work to get them to disperse in water. So the application for these clays from the Georgia Kaolin Company was not ceramics but paper, right? And so the coarse-grained soft clays were really the preference because they could be easily processed, easily dispersed, and when you disperse them, you can remove the stuff that you don't want, like quartz particles. Okay, and then that material goes to be calcined to give a calcined kaolin. It goes to make paper. So the coarse-grained clays were the preferred clays. Now there is an argument that there are not as many coarse-grained clay deposits left in Georgia. True, but recognize that these deposits are not small. These are massive deposits. Okay, but you'll see both. And the interesting thing is the fine-grained clay here. That's actually much more like the fire clays that we see in Missouri and other places, because the fire clays tend to be, the term is gritty. They tend to be coarse. They tend not to disperse well, which for making refractory brick nobody really cares, right? And if you get one that is coarser grained, it's called a plastic fire clay. So they have names for all these things, but they're really reflecting the nature of that material as deposited. And my suspicion is that you have more dissolved salts in the fine-grained clays, and those dissolved salts are tending to stick everything together. And so then you have the problem of poor dispersion having to work at. Don't care for that picture. Really like this one. I guess we can look at the other one and see what it looks like. This is a very fine-grained clay. You can see the 1 micron size bar down at the bottom. The resolution isn't very good. But this is telling us basically, they're called clay booklets. I have some other pictures of them. Really nice pictures of them. That's a pretty huge size bar. So what happens is on the surface of feldspar starts dissolving, the potassium leaves, and then you start to precipitate this clay crystal on the surface. And then it's formed on the surface. And then because of the mismatch between the octahedral and tetrahedral layers, you start building up strain, and that crystal will cleave. It stays there. Another one forms behind it, and then it cleaves and it stays there. So you build up crystals, you build up booklets, and these crystals like this. Okay? So you're basically, it's like an accordion, if you will. They're just boom, 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 up on the surface of that feldspar particle. And when you throw this stuff in water, these booklets typically break up on their own. They're pretty easy to redisperse. They're not really connected between the particles other than a weak attraction force, van der Waals and what have you. But you put them in water, and even a little bit of chemistry, shift in pH, they'll redisperse. Adding dispersant, they redisperse. Okay. A little bit of agitation, they'll shear and disperse. So they're really easy to disperse. As the clays get smaller, that attraction is greater per unit volume or mass, and they're harder to disperse. But there may also be other things such as dissolved salts. Okay, so I'll show you now a primary clay deposit. The projection on my screen is better than this. I'll post this on Canvas. The images are pretty good. So this is in Sparta, Georgia. Saprolite is the name for the material that forms the kaolinite, or the kaolin deposit that forms. Sparta granite is the outcropping. Okay, so basically, I'm a ceramic engineer at a clay conference, and I'm surrounded by clay geologists. They see the world differently. I think that is an accurate statement. All right, so here's the story. So Tom, I had been meeting with Tom about a problem in dispersing clays for, it was BA, no, it was Hammond and Gillespie. And they were changed dispersants. In the process of changing dispersants, they started to precipitate a new particle which was sticky. All right, now why do you care? Well, they want to beneficiate and remove the quartz. I talked about making paper. You can make a mile of bad paper in a couple of minutes, basically, based on coating speeds. And quartz particle lodges under that blade, and you're making a line on the paper. You can bump the blade, so you basically let the blade jump, and the quartz particles will clear. These particles that they were producing won't clear. They stick to the blade. So when you bump the blade, you put it back down, the particle's still there. Right? So for the people who were buying their clays, who were making paper, they really didn't like that, because what they would have to do is stop the coating process and literally clean off the doctor blade, right? And in that period of time, you just, you stop making, 10 miles of paper or whatever. So it became a real issue for them in the marketplace. And we think what was happening is that they were precipitating calcium phosphate particles because they had changed from sodium silicate as a dispersant to sodium phosphate. And so we made some calcium phosphate here, and yeah, sure enough, it sticks to everything. It's really interesting it's more or less an amorphous dispersant, but it would form these little spheres. Anyway, Tom, we go on the field trip. This is the field trip. He says, this is Tom's term. He says, when you see this, it becomes abundantly obvious that clays come from granite. Okay? And which was interesting. And what I wasn't really prepared for, if you look up here in the upper corner, right here, this is the bus we came on. So this is the first stop. You drive up in the bus. It wasn't supposed to have been raining at this time in Georgia, but it had been raining. So the bus had some difficulties, and all these clay mineralogists are on this bus, and me. And so I'm sitting next to Tom, and the bus stops. I'm not making this up. Out of nowhere comes picks, geology picks or whatever, hammers, and plastic bags. And these guys, mostly guys, they jump up, they literally run from the bus to this clay outcropping. I'd never seen anything like it. Not only that, I felt naked. I didn't have a pick. It didn't occur to me to bring a pick. I didn't even have a plastic bag. I was completely unprepared for this event. Tom, however, somewhere from Tom came a pick. I don't know. I didn't see it when we got on the bus, and plastic bags. So I still have samples somewhere of these clays in the back of Tom's car still, probably. And that was 22 years ago or something. Anyway, they are probably still in the back of Tom's car. But you go up to this clay deposit, and it makes sense. You can see, and I'll show you that here. So where these people are standing is they're actually standing on granite. This is a lake, and this is actually the clay deposit here. Okay, and the top, which is only maybe at most a meter deep, is the overburden where the trees are growing. So it's really cool that you can see, and you can go right up to this face, not over here, but right up to this face here. And what you see is this basically. This is that clay deposit, and Sam Pickering there's a booklet I'll post for you on Canvas called, I don't know what it's called. Anyway, Sam Pickering was a state geologist for Georgia, and he conducted this tour. But this is all that clay, and the white areas that you see are where these clay mineralogists have beat up the front. They just come at it to get samples that they can take back and play with. So, but you get an idea of the depth of the deposit. Now, the thing that I find interesting is you can see if we go back to here, you're looking at a person, say 6 feet, you're looking at roughly, almost 30 feet of clay, right? So it's a nice deposit. And the takeaway message is, yes, it's a nice deposit, but it's not big enough to justify commercialization. So this looks like a great clay deposit, and there's a lot of clay here. It's just not enough. It's like the argument of making cement from, you have to have a huge amount of material. So this is, if you can see this well, This is the clay that literally was just knocked off of that deposit next to the granite that it came from. It's probably better on my screen. And what you see is that they look the same. I mean, it's clear that this morphology and that morphology is quite similar, but the pink that you can't see here becomes the white of the clay. Even the quartz particles are the same size and morphology as the particles that are in the existing granite. And then in the process of walking across that granite shelf to go back in the bus, you recognize that the granite you're walking on is converted to clay. You can see the surface has been altered and is still being altered, that the process is continuing and will continue for a million years or whatever until they run out of the granite. So this is a close-up of that fabric. Okay, so it says the granite fabric retained in the saprolite. So if you didn't know that this was clay, you might argue that it was granite. So the deposition is immediate; it's right there, and it's simply water getting down and dissolving that sodium out, or the potassium out, and facilitating that conversion into clay. Those two things are necessary. The rest of the deposits are secondary deposits. So this is in the Jeffersonville member, the Huber Formation. Those are all geology things. So I didn't even bring a camera. And cell phones didn't have a camera then. I'm not even sure I had a cell phone then. But there was another guy there, a geologist. He sent me copies of all his photographs. And so he labeled them all, so I just used his labels. But the geologists tell you the formation it came from, what the deposit is, all that kind of stuff. And to me, this is a secondary clay. So what you see is, this is the clay that's being mined. You look at it, well, that doesn't look nearly as deep as the other one, except it's a huge area, acres and acres of land. And then this is the overburden. And you can see the banding in the overburden. And the banding is then other deposition events. So the clays deposit more or less in lenses. So the clay comes down, hits salt water, starts to build up, goes in a depression, it builds up, and then some other geological event happens and the process stops, and then something else deposits on the top. So you get this banding, high iron or more iron, low iron, and you can see the trees and the foliage on top. And then here you're walking around in clay, and when you look at this, you recognize that if it rains, you just got this huge, acres and acres of slip and slide. There's the fine grain structure. So if we looked at that and we compare it to this, right? This is more coarse grain clay. Primary clay. So one of the arguments was that primary clays are coarse grain clays. It's not necessarily true. And then here is a finer grain clay. This says clastics. This is the overburden, and you can see the lens shape morphology of the deposits. The clays that are on top of the kaolins that people wanted, those clays on top were often used to make kitty litter. So kitty litter, they take the clay and they heat it and it expands, typically montmorillonitic in nature, and by heating it and getting it to expand, you increase the surface area further. Clays are really good for absorbing all sorts of things, including organic molecules that are responsible for odor. So it's a interesting setup. We did some work. There's a place called 9 Sigma or something like that, and it's sort of a research clearinghouse looking for consultants. We did some work on kitty litter a while back, and Had and I had some ideas and met with, I think it was the Clorox people. Who makes Clorox? Johnson & Johnson or something? So here's the most entertaining thing. They will ship you cat urine in gallon jugs, typically frozen. I mean, there's just a whole disconnect here, you know. I have a really funny story, but it's sort of along the same lines. How do you get gallons of cat urine? I mean, you know, do you squeeze the cat? I mean, what are we talking about, right? I mean, no, I'm serious. Like so we were doing these experiments on clays and some other things, and they shipped us cat urine. Anyway, I have another funny story about a dog that I'll tell you afterwards. So it doesn't have to do with urine. So, am I here now? So we have a new puppy. We got her in March or so, something like that, or April, I don't know. So I take her to puppy school, which is really about training me rather than training her, you understand. It turns out I am partially trainable. And anyway, there's this woman in this class. There's 5 people in the class and 5 dogs. And she has this little puppy, which is a holy terror. And she says that her other dog died. And the day her dog died, his name is Laser. I can't remember the new dog's name. Says that she went online and couldn't find a dog other than a puppy for $5,000. She goes, I'm not going to spend $5,000 on a puppy. So then that night, Laser comes to her in a dream and tells her to get this dog. So she goes online the next day and here's this dog, and she gets it. So my only question is did his lips move? You know what I'm saying? I mean, did he draw a picture of the dog? How did he communicate to you to get this dog, right? So anyway, I did have, though, I had my act together. I didn't actually ask. So, in a rare moment when my tachometer was working properly. So, you can see this contact area between the clays that are higher iron-bearing clays and the clays that are of interest, and how sharp that transition is, which is quite remarkable. So in the process of mining these clays, it's very easy to remove that top material and begin to just clean kaolin. The other thing you can see here is this is not a hard rock mining operation. You know, a shovel works. And a backhoe or a bulldozer or whatever is very effective at mining clay, which tells you that unlike the materials that are sitting here in front of us, right? I mean, this is hard rock mining. Right. So you drill holes, you blast, and then you crush. Clay comes out of the ground in a form that is immediately dispersible or usable, that you don't need to do all those other things that you would have to do with quartz and feldspar. This is teokaolin's Sarah Duke's mine means that it's something, either the person's land or a name of an area. That's what it is. Twigs refers to the type of clay based on where it came from. Reduced, hard, fine kaolin. And the reduced clay means that you have iron in the clay in a 2+ oxidation state rather than 3. So in its deposition process, it was somehow starved of oxygen. Okay, and so you get a reduced clay. But what I want you to get out of this is the scale. Okay, this is a good size deposit, and they're mining this. You've got a backhoe in the foreground. They're mining this area, and it's large, and it's not the whole deposit, right? And they have, your road going down is all on clay, and so and you'll see another picture later that they would often mine. They slurry the clay and pump the clay as a slurry someplace. They may put it in trucks and transport it to a processing facility. Sometimes, depending on the size of the deposit, they'll build the processing facility right in the mine. So the other thing you can see is, by the way, in the top of the image is that there are clouds on the horizon. And I've never been in a group that paid so much attention to the weather. I mean, these people were all intently paying attention, because if it rained while we were in there, it would take us a long time to get back out. It's really fascinating. All these clay mineralogists were really nervous about the weather. It's really entertaining. There you see also the quality of that clay. And the next image shows that these are marine deposits, which is not a surprise. Shrimp burrows, and these are shrimp burrows that are 1 million years old or whatever, and they show up in the clay. And there's a discoloration region around that, which you can probably see. But they know to look. I didn't even know to look for these things, and they're showing us. So this next image is interesting because this is the largest kaolin mine in the world, and it's ECC is English China Clay. They own this mine. This is in the Georgia Kaolin Group, or was, and it's called the Buffalo China Mine, and it has nothing to do with Buffalo, China. It is the Buffalo. What's it called? There's a Buffalo Creek Formation, and this is a China clay mine. So it became the Buffalo China Mine. Okay, so it's not about Buffalo, China, but this is coarse grain, soft kaolin. This said it's Old, I don't know what that means. They're all old as far as I'm concerned. You know, the funny thing is, like, what's the oldest thing in my collection? It's probably sitting here on the table, right? So this mine is massive, and it's so large, and there's so much going on that we were not allowed down in the mine. So we were able to come to the edge and look. And so, but you can see, that in this image are things like, backhoes and trucks and stuff like that. It's just an immensely huge deposit. So what they did, though, is out of this mine, they brought these big chunks, and you can see the fracture pattern. The conchoidal fracture is characteristic of a coarse grain clay, and they brought this up. This is right out of the mine. Nothing's been done to it. This is the way the clay comes out of the ground, so you get an idea of the quality of this clay. The other thing you see is there's no evidence of quartz, right? I mean, it looks absolutely like only clay. Now, the entertaining thing about this is that the Clay Mineral Society produces a number of what they call source clays. So you can go buy clays from them that are very well characterized. And KGA1 is kaolin, Georgia #1, and KGA1A, so there's a modification. KGA1A is this clay. And so it is, and then you have KGA2 is a fine grain kaolin, KGA1A is a coarse grain kaolin. It's this clay. So all these clay mineralogists are out there filling their plastic bags because they got to pay $30 to get a sample, and now they got as much as they want. So it's really entertaining to watch all this go on. But you can see the quality of the clay. Okay. So then here's another mine, and this, you can see there's water in the bottom of the mine in here, and then the mining operation. And this is one, I think, where they had down in the mine a processing facility. And then they go to storage, and this is Wilkinson, which was a clay company, produced, I think they used to produce tile kaolin #6, which is a really common clay for us. We use it, the artists use it. It's not particularly plastic, but that doesn't make any difference to us. And what they would do is they would mine the clay in stockpile, as I told you about, right? And then they would blend from here. And this clay has a lot of smectite in it. So smectite drives up the methylene glue index, which we'll talk about, the cation exchange capacity. So what they do is they'll take that clay and they'll blend with clays with low smectite levels to tailor that cation exchange capacity value to match, to ideally give you uniform properties in the clay. Dry branch kaolin, the Brooks mine, and this does have that processing facilities here, and the material is basically processed here. This is a water storage tank, and then it gets pumped out to the mine facility or the processing facility. What they would do is they would mine layers, right? And then as they progress down, they've actually mapped the whole area, and I'll show you that in a moment. They map the area and they know how deep the deposit is and where they're going to mine. And then they mine until that deposit is done, and then they'll close that up and they'll go to the next region. So you can see, though, that there is a lot of clay. This says blunged on site, transported slurry form to a processing plant. Very efficient means of moving that material around. The other thing they do typically is they recover all the water and they reuse it, so they don't have this sort of, let's take it out of the river and dump it in the river someplace else. And there's a lot of regulation, but they're very proud of their ability to do that sort of thing. Ozone sparging. Ozone sparging is they bring in ozone and it reacts with the iron to reduce it to improve the whiteness of the clay. That is a relatively new technology that allows them to mine clays that otherwise wouldn't have met the whiteness specification. This is drag lines, so they're sieving that material in slurry form to remove the quartz. It's a relatively efficient process. There's also hydrocycloning being done to do the same sort of thing to eliminate sand, because sand's a problem. Okay, and then here they're very proud of this. This is the last place we went. This is that processing facility has been there for over 100 years, but they reclaimed it, made a lake where the pit was, threw fish in it, and planted grass around it, trees and stuff. Not many trees, but some. So, and now the locals can take their boats out on the lake and fish. Everybody's happy. Sorry, that color scheme is terrible. Jason McCutcheon is worked for HC Spinks. Sorry, you can't read that. It's clear on mine. Quality control and mining and processing bulk clays. So in 2000, I organized a symposium, American Ceramic Society on clay, and brought in people from industry. And a lot of these slides that I have been showing you, the structure of clays, came from a guy from Vanderbilt. Jason, this is how they mine. So there's this process flow chart. I'm not going to go through it, but specifically what they do is they'll go through and they'll drill holes, and they'll look at the quality, and they'll look at the depth of the deposit, and they'll build a map. Okay. Then they go through an iteration process of flow chart. Is there sufficient quality? What's the depth? At what point does it become economical? So the economical is how deep is the deposit, how much overburden is there, how much I'm going to spend to remove the overburden, and then how much clay can I get out, and if that ratio isn't right, they just won't mine it. And then look at the quality of the clay, and if the clay requires a lot of processing, it might sit in the ground for another 20 years before it gets processed. So they do pre-mining, they drill, okay, and then they look at it. If it looks good, they'll come back and drill another set of holes that are tightly spaced, more tightly spaced. Then they'll take that information and create a three-dimensional map that shows the depth of the clay deposit and the quality and what's above and below it and all that kind of stuff. And they develop then a picture of what they're going to mine. And recognize this is this information is almost 20 years old, and so it's only gotten better. Okay, now, and even at that time, on a front end loader, they would have a GPS beacon, and it would literally tell the driver where to go dig. And that was 20 years ago. Now I assume they just do it with drones and don't go in the mine. I don't know what they do now. So this is an example. This is the spacing, the holes. This is designating the hole, 97, 17, 97, 10, 97, 6. So you have 17, 18, 19. You can figure it out. 97 is probably, I don't know what the 97 means. It doesn't make a difference. And then those are the location of the holes. And what they'll do is they're 150 feet apart, but they'll take samples every few feet along the core that comes out. Okay, and they create this map. And the map shows them then, you see they drilled a lot of boreholes, okay? And then, if you do the math, you're looking at regions that might be, 1,000 feet or several thousand feet, even a couple of miles in area. And when you look up in this area here, you'll see the colors, right? And if we zoom in on this area, you can see then, here's that. These are those color regions. These are the mining campaigns that occurred in those different regions based on this area. So they looked at this area and they built their map, and then they went in and they started mining. And so if you look at, it may be hard to read from where you are, but here's void number 1, which says September 98. Here's void number 2, 1198. Void 3, now there's a gap, and now we're into March and April. Void 4 is in the summer. Void 5 is again in the fall. There's a gap again. Here's void 6 in November. Void 7 is in the spring. Okay, and this is more or less where they're at, and then this is the direction they're going to go. And so they start mining, and then they move to the next region and they mine systematically. But they don't mine continuously all year round because of rain. And this is in, so HC Spinks is in, I want to say, Tennessee. This is on the other side of the Appalachians. Okay, and there's just an example of the borehole maps. But then this is what they generate, the 3D model, and then I don't know what the colors indicate. It's not particularly important. But from this, they'll estimate the tonnage. They'll predict the timing. They'll do long-term planning, and then here's your general map of dimensions. And down here, the color coded map tells you the depth of the deposit. So from 0 to 2 feet, which is not a value, to 14 to 16 feet in depth, and where they're going to mine, how they're going to mine it. And then from those cross sections, they verify their mine schemes. And then here's an example of the model and the cross section. The cross section is what they actually found when they opened up, and the model is what they predicted it would look like, which is pretty good, basically. So this is how mining was done roughly 20 years ago. It's not changing; it's getting better. Okay, they're getting, they're very efficient at this, and the reason that they need to be that efficient is because there isn't much margin on what they're producing, right? You can sell clay. Used to be that clay delivered into Buffalo at $120 a ton. Okay, they're not making $20 on a ton. They're making a few dollars maybe, right? And so anything that you do to make that process more efficient goes to your bottom line. But you have the same sort of problem like we have, where like with Walmart, everybody's pushing them to reduce costs and reduce their raw material costs, which, as I showed you before, is sort of a waste of time in many respects. You pay 6% for your raw materials, you shave that down to 5.5%. It's not much. You're better off to improve your process. And there's the clay mining aspects of it, which we've already showed, basically. Okay, so clay stockpiled in the shed, and then what they do is they blend that clay on the floor, and the way they blend it is by front end loader, shovel fold goes into a blending, large mixer. It gets blended in that way. 1 from here, 2 from this pile, 3 from the other. They get blended together, and then they go in to be bagged or put into rail cars or super sacks or trucks. Okay, and the blending. So the takeaway, everybody blends. Okay, everybody blends. The only people who don't blend are basically the artists who go over to the hillside and literally dig the clay themselves. Okay, which by the way happens around here. They blend because the way you sell clay is based on consistency. And what you want to do is you never want to have a clay coming from a single mine location, right? So that means that you're going to mine this clay and you're going to hope that that deposit stays uniform. It will not. It's going to vary. It could vary based on deposition depth. It could vary based on the horizontal variation, the geography of the deposit. And so what you're going to do is you're going to open up these patches and you're going to have a pretty good idea of what it looks like. And then at another location, even maybe in another mine, but maybe another location in the same mine, you have a very different chemistry and mineralogy for that clay. You're going to bring them together and you're going to blend them to keep that clay uniform. And then as this clay starts to move and the other clay starts to move, that what you're producing is not moving because you're changing your blend to keep the properties the same. And there are the companies that are doing this, like KT Clay, Imerys, etc., have been producing uniform clays for a very long period of time. And that's the reason they're able to do that is because of blending. So we have old mine number 4, and then the entertaining part is the folklore says, "Oh, well, old mine number 4 isn't as good as it used to be." Nonsense. Okay, those clays are remarkably consistent over time, and if you want to look at that, we have a lot of data that we've collected over the years on clays, and what you find is their chemistry stays similar. Their other properties stay similar. Their surface areas are remarkably consistent. Right, and they're blending to keep that clay the same. The other thing is, I think I told you this, right? When you have a problem in the factory, the first thing you do is blend the raw material supplier. And so the raw material suppliers have gotten really good at documenting and demonstrating to you that this was not our fault. We are producing the same thing that we produced 10 years ago that you've been using all this time. So it wasn't an excursion in the clay. Quality control summary, basically you drill samples, you look at the, before you mine, and then you blend, and then you look at the product and the monitoring. And then he has, so this is basically a stockpiling situation. Now, as I said, you're going to mine all that clay and you're going to stockpile it. That's all great. When you go back to the mine, though, now you see a variation in the mine because of the rains and the washing of the clay and the changing of soluble ions and salts in that material. So, beneficiation process. This is actually very likely for HC Spinks. So Spinks produces clays almost exclusively for the sanitary ware industry. So what you find is teal kaolin, a lot of these clay companies are geared towards a specific industry, which isn't a bad thing, and it makes sense if you think about it. So what they do is they tailor their products based on the industry that they're serving, which makes a lot of sense rather than deciding you're going to produce a clay for everybody. So the sanitary ware industry is looking for something in terms of the clay, usually suspension behavior, the ability to get high solids loading with relatively low viscosity without sedimentation. Okay, that's what they're looking for, and they're looking for coarser grain materials that facilitate the casting process. Okay, fine. When you get into dinnerware, electrical insulators, they might be looking for clays which have a little more stiffness and plasticity, pack better, finer grain would be okay. You know, so they're going to be targeting those clays, and then the producers of those clays are targeting that industry. Then you get into the tile industry; they don't care one way or the other what it looks like, apparently. Okay, so there's this progression of ideas in terms of what you want. They will beneficiate the clay based on that industry. So when you get into paper clays, you can buy the clay dry, or you can buy it in a slurry form. And a lot of companies have chosen to go the slurry form because they have no process when they get in-house. They can bring it in, they can pump it into a storage tank, and it goes right into the process. They don't have to deal with it. So this is sort of the overall beneficiation process. This is interesting because this is talking about like a washing process for mining, which we rarely see that I'm aware of. Most of it is to be mined and then slurry processed later. It says, I assume this is so we have an angled repose. You're going to cut back the overburden, so if it rains, it doesn't wash into the mine, basically. Basically, what it is that you're going to go through these different sedimentation processes. You disperse the clay. You'll do things to remove the grit. There's a note right here that says hydrocycloning. Okay, the hydrocyclone is a way to remove grit effectively. The material that comes the overflow, which is a coarse, or I guess it's the underflow, the coarse fraction goes to a settling pond. That's mostly your quartz. The fine fraction goes into the process, and then they dewater these, and then those materials go in to suspension form. And so they're processing this material. They're recovering the water. They're reusing the water in the process. And then they're removing the fines, and the fines go to basically a sedimentation pond, or the coarse, sedimentation pond. And then eventually that gets filled in, and they make a lake out of it, or farmland or whatever. And then phase 2 has to do with blending. So this is from Spinks. So they're now blending not shovelfuls, they're blending slurries to get a uniform suspension that may go directly to a sanitary ware company. So they may actually buy the clay in a suspension form, or they may buy it dry and redisperse. So, and recognize it costs a lot of money to remove water. Okay. And then this is more of their flow chart, which we're going to ignore. Okay, so particle size, specific surface area, those are big. Residue on a 200 or 325 mesh. The chemistry is measured, the LOI is measured. Sulfur and carbon level affect how it behaves sometimes. There is a correlation, not a good correlation, but in the industry there's a correlation with sulfur and dispersing ability, and it is false. Okay, so they do a test for sulfur level, and they go, oh, okay, this kind of works. Works about 70% of the time. And the assumption is that the sulfur is controlling the rheology of the clay, which it is not. It's what the sulfur comes in with that controls the rheology of the clay. So it comes in with sodium, it's less effective, it doesn't have much effect at all. It comes in with calcium, it's a big effect because calcium coagulates the clay. I'll tell you about that later. Fired color is a big one for us. Casting rate, modulus of rupture. So the cast bars, they don't cast them typically out of just clay. They're typically a mixture of clay plus quartz. Okay, because the clay by itself, if you extrude a rod of clay by itself, it's very difficult to get a good quality rod for mechanical testing. So they'll blend with 50% quartz, and then they dry it and they measure the green strength. The value, frankly, means nothing. But you're talking about an industry that has a lot of folklore, and you're going to go, look, my clay is stronger than this other person's clay. And the argument is, oh, finer grain, better plasticity, stronger clay. Not necessarily true. Other things contribute to that strength. And then moisture retention, which usually scales with particle size. I like this. This is how it used to be. You have a electronic transit to an HP calculator, it goes to a computer. I think all that's probably now done on a cell phone. Okay, so, and I think you probably just go up and take a picture of the deposit and tell you where to mine. I don't know. So, mineralogy. So, there were 3 science whiteware. 2 of them were published as proceedings, science whiteware 1 and 2. Science whiteware 1, we brought in a lot of people. The book should be on reserve in the library. I copy chapters for you when appropriate. Science whiteware 2 was primarily focused on the front end of the process, raw materials, informing processes, colloidal behavior, etc. Science whiteware 3 was on the firing end of the process. So Jessica Elzier was at Teal Kalin. She did a lot of work. I met her at that clay conference in Ottawa, and she and Tom Dabrowski went to school together. A bunch of clay mineralogists came out of University of Indiana, and Hayden Murray's program, if you run across that name, it's in the Science of Whiteware. We brought him in. Pictures of the clay, we like that, that's fine. This is how they look at it. So Teal Kalin is looking at this. Teal Kalin produces clay for the paper industry. So they look at the clay differently than people who were producing clay for the whiteware industry because their goals are different. Teal Kalin did, so this is a general breakdown of the mineralogy of the clay. So this clay is not the kaolin that comes out of the ground. This is a processed kaolin already. How do I know that?
Just not enough quartz?
Yeah, there's almost no quartz. So they've removed the quartz. So the quartz shows up in the Georgia kaolins. They just remove it, okay? And the quartz shows up in the ball clays, and they don't remove it. So the ball clays, you can have 25 to 30% free quartz, and the kaolins you have a trace amount of free quartz because they typically remove it. So what I'm going to do is I'm going to stop here since there's people outside the door, and that clock is off. I apologize. And then if you are interested in the gravel pit, if we can accommodate you, are welcome to go. It is tomorrow. We meet out front from here at 2:15. Okay? And what I would ask you to do is if you come to the gravel pit, want to do the gravel pit, hang out outside the bus until we do a head count so I know that we have enough hard hats. Because they won't let you go through the mine without a hard hat. Good? Great. Have a good weekend.
There's a